Yes, yes, you're on. So I hope I'm audible right now. Yeah, yeah. Thank you for the nice introduction. Moitrada is a very, he already talked about me, so it should be nice if I should also talk about him. He's an outstanding mathematics major uh, in currently studying in Indian Association for the Cultivation of Science, and as a dada, as a guide, and in all aspects, he's a very nice person. And currently he's the most remarkable thing about him is that he's so much open to all sorts of different fields, like being a math major, he's doing his ms thesis in the intersecting region between maths and physics. Okay, so that's something about him, and he's an outstanding person. So let me start without further ado. uh, let's see. Okay, or tab, this one. Let me know if my presentation is visible. It's visible, right? Okay. 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 So I hope I'm also visible, right? My videos. Okay. Okay. Good enough. Good enough. If there is any meetings in the chat box or anything, just let me know in case I fail to notice or something. Okay. So let us start. As the title of this presentation, it's pretty much, I don't know if it's clear or unclear. Let's see. It says that linking Newtonian mechanics to Newtonian optics. Now, what do I mean by this? Basically, Sir Isaac Newton, two of his greatest contributions are in the field of geometrical optics. The one which you know as ray optics have been studying since class 9, and the other one is the Newtonian mechanics, basically the three Newton's laws of motion and Newton's gravitational law, which of course he said that he could be able to derive by standing on the shoulders of giants, by which he meant, of course, Kepler and Galileo. So, obviously, Kepler was a giant. He did a huge astronomical observation. So, let us move on. What exactly do I try to uh, am I trying to present over here? How many of you have actually heard about something called the variational principle of Lagrange? Maybe a lot of you have heard. If there are first year students who might not have heard, might have heard, I don't know. It's something that can be used as a tool to connect these two regimes, which might seem completely unrelated. Okay, so as you can see, we have the different paths. let's get off with it. Huh. Now, variational principle is something that Lagrange gave, and before Lagrange, one of the first, you know, principle of quote unquote least action, it's a misnomer because it's stationary action, was given by Maupertuis. And this principle of least action is considered a principle. Principle in the sense it's something that cannot be questioned, as if it's a law, it's a sacred law, something biblical, as if written in the, what to say, a religious textbook, Bible, Gita, Quran, whatever. So it's like a law. It's something that follows. I mean, nature follows this law. So let's see what Maupertuis had to say. Obviously, you can read this. He said that our principle, more consistent with the ideas we ought to have of things, leaves the world in a continual need of the power of the Creator. Great Creator comes in instantly and is a necessary consequence of the wisest use of this power. These laws, so beautiful and so simple, are perhaps the only ones the Creator and Ordainer of things has established to affect all the phenomena of this visible world. Now, that's what Maupertuis said. He felt this principle to be a godly principle, that something like action or some quantity minimized is something that just nature follows. Let us try to put in an intuitive reasoning behind it. Like, let us start questioning God. Let us start questioning why should we have a variational principle in the first place. Maybe we might find some logical reasoning to it. So that's it. Can we have a more logical ring to it? What if we try to justify an external path? Sure. Now, what I'm going to say is, let us, what do I mean by path, firstly? For our first year undergraduates, I mean that a particle is going from one position to another, one place to another, and that is what I mean by path, in the sense it tries to go through some potential distribution, having a particular energy. It goes through a path, its trajectory basically. Up to high school, we know that is defined by Newtonian mechanics. Eventually, we can also find that this path can also be described by a principle of stationary action, or a variational principle, often it's known as. But let's not get into too much details because I have the entire mathematics worked out for you to see and understand. Over here, I try to explain a wave theoretic approach of the extremum path. You can see a start and an end point in the slide. You can see two black lines joining the start and end point. There are two different paths. Now, you should have heard me by now repeat the word variational principle again and again. Variational, variational, variational. You see that there is a red path and there is a blue path, which is slightly varied from the black path. By this I mean that by slight variation, I am trying to obtain an infinitesimal variation. That is what I'm trying to say in the black path, by keeping the starting and the end point fixed. This is what we should try to appreciate, that this is what we have as of yet, because it's going from one point reaching another point. In between what path it will take, that is what I'm trying to determine. Okay, so I make slight variations. The reasoning that I wish to apply is that think of this black path as a wave. Now, wave we know constructively, destructively interfere. Maybe to some extent constructive, to some extent destructive interference. These things always happen. Now, what if there exists a black path, and by slightly varying the black path, the infinitesimal variation, the length of this path does not change? Try to imagine it again. Let me repeat. This one path, black path, I vary it slightly, very slightly, I mean infinitesimal variation, and the path length does not change. If the path length does not change, And remember, this we are considering to be a wave. So if the path length does not change, then the phase at the end does not change, right? So you can communicate over the messages, in call messages. Okay, might be that I'm not being able to see the messages, so you can communicate. So basically, there is a path, there is a wave, slight variation, the path length does not change, and hence there is no phase difference between the black line and maybe say the red line over here. Maybe say the red line. There is no change in that. What does that mean? That means in the infinitesimal neighborhood of this wave, there is constructive interference, 100% constructive interference, and anywhere else there is not 100% constructive interference. There might be 89%, 80%, who knows, 50%, 40%, even destructive interference. We don't know. But the path along which, if we do introduce a slight variation, the path length does not change, implies that the phase does not change. So we say that the wave exists only along that path. Okay? Is everyone satisfied with it? You can write any problems in the chat box, allowing you to absorb it for a little bit. Okay. I am assuming that everyone understood this. Anyways, you still have time later on also. You can ask me anytime. This is what I have explained over here. Every one of you, I guess, can read it. Simple thing. Constructive interference of waves occur along the neighborhood of a path about which infinitesimal variation of the length is zero. Hence, the wave exists. Elsewhere, we can imagine that destructive interference occurs at least to some extent. That means I'm not saying 100% destructive interference occurs if the wave does not exist. No, the wave exists, but destructive interference occurs only to some extent. Okay, let me pause here for a bit. Try to appreciate the logic behind it. That in such a case, what is happening? This is just a logical ring that I'm trying to put through, that actually Evans and Rosenquist have tried to put in through in their paper. None of this is my work. I'm just explaining this, okay? Because I found it interesting. I'm giving this talk at this point. Okay, let us move on. So, what is the phase and path relation? Phase is phi, we know, and we know phase difference. Delta phi is 2 pi delta x by lambda. Everyone agrees? You can write in messages. Okay, you can raise hand, you can write messages. I can sometimes see it also. So the phase difference delta phi is 2 pi by lambda times delta x. Now 2 pi by lambda is all we all know is k. If there is a wave of the form a sine omega t minus kx, then 2 pi by lambda is denoted by k. And then the delta x, I'm moving over a continuous format fashion. I can write d phi is k dr. R over here is the infinitesimal variation path that the whatever that the wave has traversed. Okay, that the wave has traversed. Light wave is what we are talking about. Formulating a variational principle for light path. That's the heading. Okay, so if this is so, then k we know is omega n by c. I'm not making any assumptions here. Okay, k is omega n by c. How is it so? Let me clarify this a bit more. What do we know about velocity of light in a medium? Velocity of light in a medium is what? Omega by k. Am I right? Velocity of light v is omega by k. So if velocity of light v is omega by k, and velocity of light in a medium v is what? C by is Velocity of light is n times c or c by n or n by c. What is it? Try to think. Relation between refractive index, speed of light in vacuum, and the speed of light in vacuum and the speed of light in medium. N is c by v. If n is c by v, then v is n is c by v. Then v should be c by n, right? I'm writing it in the chat box. Let's see. V equals c divided by n. Um, n equals c divided by v. Good enough. If n is c by v, because refractive index is a number greater than 1, therefore this gives me velocity of light v in a medium is equal to c divided by n. Good enough. You can look at the chat box if you want. And velocity of light v is c divided by n. And we know v is also omega by k. Therefore, we can write k equals v by omega by v. K equals omega divided by v. I'm just doing this so that no one has any confusion for why this had happened, why that had happened. Omega by v, but v was my c by n. Therefore, my k comes out to be omega n divided by c. Right? So my k comes out to be omega n by c, out of which omega is the frequency of the light wave, which I'm considering is not changing. It's a coherent source, frequency of the light wave, and therefore it is a constant. C, speed of light in vacuum, is a constant that comes out of the integral. And we have phase, that means this is basically change in phase, delta phi, from the start and end point, is omega by c integral in refractive index as a function of space modulus dr. Why mod dr? Because we are taking the magnitude of the path length, the entire path length we are going through. Okay, good enough. Now, what we are saying is that the constructive interference, 100% interference, can occur only along that path through which, if you do a slight variation, an infinitesimal variation, the path length and hence the phase does not change. Okay, phase does not change means the variation in this integral quantity should be zero. That is, I'm saying, since constructive interference can occur, basically reading out what is written in the slide. Okay, so the variational principle can be seen as I put a variational delta for the variational principle. Integral nr mod dr equals 0. So I hope we can agree up to this point, everyone. Does anyone have any questions at this point? You can write in the chat box. Okay. I'm assuming that no one has any questions. So let us move ahead. Ah, there's a famous drawing by MC Escher, because I'm going to introduce a parameter called the stepping parameter. I gave an image of very intricate steps, confusion, basically to denote that it might be very confusing, but at the end of the day, you'll get it. If you have any problems, ask me. Okay, so we know that uh, any trajectory can be parameterized, right? For example, what is the parametric equation for a parabola? It is, I mean, y is equal to some, I guess, 4ax square. Yeah, 4a y is equal to, yeah, that 4ax square. I guess it is 80 square comma 280. I mean, there is a parabola or standard parabola that we learned in high school, and it can be parameterized in terms of a and t, right? So the parametric form would be x is equal to 80 square and y is equal to 280. So that over there a and t were the parameters. So similarly, any trajectory of a light ray r vector. Okay, one thing to note is the bold font represents a vector, and non-bold fonts represents a scalar quantity. Okay, or classical physics vector, normal vectors, a Euclidean in a Euclidean vector space. So this r denotes the trajectory of the light path, and r is a function of x and y and z. Good enough. Now x, y, and z, each of them can be expressed in terms of a parameter a. I'm assuming. I have not defined what this parameter a is, what this is. This is an arbitrary parameter a. We can write it like this, where r is the position of the light path in space, medium, etc. etc. Then what I do, in our previous variational principle, what we had said is that delta integral nr mod dr is equal to 0. Now we are saying delta integral nr mod dr dA is equal to 0. We can do this simple because r is a function of a now. Next, what we do is we go on to defining the stepping parameter. Uh, what is the stepping parameter? This a. I'm naming it as the stepping parameter. It's not I who has given this name. It's Evans and Rosenquist who has given this name in the 1985 paper. Name this stepping parameter. Why stepping parameter? I don't know. God knows. But just let's consider it as a step to move on to our next situation, next scenario. Let's see. So, an outrageous assumption, an outrageous definition, rather, we should say, has been made on this stepping parameter, where this position of the light ray is as it moves, the position of the light ray is denoted by the vector r, and modulus of dr dA to be refractive index n. This is how I'm defining A. I'm defining the stepping parameter A such that mod of dr dA at any point for the light trajectory gives you the refractive index at that point. This might seem outrageous because such a parameter we have never come across. We have come across parameters like time in our normal mechanical case, where trajectory x, y, and z of a particle, the coordinates of a particle, can be written as functions of time. So, if you know the time, you know at what exact position the particle is, given the Newton's equations. Now, the point is, let us explore what this definition implies. This definition has some simple implications. N equals mod dr dA. I'm writing over here. N equals mod dr dA, which equals, we can obviously use the chain rule and open it. That is mod dr dt dt dA. Now, interestingly, what is mod dr dt? That is the question. Mod dr dt. Okay, here is a small mistake. It should not be c, but it should rather be v. Okay, mod dr dt is the velocity of the light in that medium. Everyone agrees? If mod dr dt is the velocity, that is the rate of change of the position vector with time. That is the velocity of light in that medium. Now, velocity of of the light in the medium is, we know, c by n. V is equal to c by n, as I have also written in the chat box. If velocity of light in a medium is c by n, so n comes out to be c by n dt dA, or dA equals c by n square dt. Check. Written over here. Now, at this point, if anyone has any questions, please ask. If anyone did not understand, or if anyone joined later, you can also ask. That's no problem. We have time. Okay, okay. I see. Yeah, parameterization, it might not be unique. Of course, I agree. The parameterization might not be unique, but at the end of the day, what do we want? We want an equation that relates y with x, right? That means y as a function of x in a 2D card. Or maybe we want a relation. We want a relation in which we do not want the value a to be there. Just like we want the equation of a trajectory. So at the end of the day, we will try to get rid of a somehow. So a is just something like it said, stepping parameter. Means it just helps you to get the final value. It might be unique, it might not be unique. We are not making any statements or any statements regarding its uniqueness. Because at the end of the day, we are getting rid of it anyhow. Just like in a time, if it had been time, then what we are interested is the equation of the trajectory. That means how the trajectory will will be in the space, how the trajectory would look. So that's it. Anything else? Anyone has any problems or difficulties?
I had a small comment regarding Moitura's question. That is, I think like by incorporating that DRDA mod of DRDA equals n, we are taking care of that uniqueness of the parameter a. Like assuming such a exists and assuming you can put it like that, I think there's only one way of doing it. Hmm.
Yeah, sure. So we have a relation between elemental change in A to the elemental change in time, and of course, like the exact value of A and T will be determined by the quote unquote initial conditions. Like in a mechanics problem, what do we have? We know dt, but we set the initial time to be zero and we set some final time to be something something, and then we integrate to get out a trajectory between that time. We can integrate a to get out between some point a initial and some point a final to get a trajectory, the nature of the curve between two a's. That we'll see later. We have not yet come to that. So this might sound a bit confusing. Let's move on. Now what we shall try to do is we shall try to construct a variation. What I have written over here is a plain and simple equation. Let's see. R is the R vector. That means the position vector of the light path. As the light is going at every point, there is the position vector denoted by R vector. I'm writing it as a function of a and epsilon. Why? We'll come to that later. R vector equals R0 as a function of a plus epsilon eta vector a. What these things are, let me just put them in front of you. R vector is light trajectory along parallel path. R0 or R naught, as one might like to call it, is the desired path. That means the path that through which the light will actually go. That means basically the solution path is the R naught. That basically gives us the trajectory, solution trajectory. That is the one through which it will go. Epsilon is a very small, infinitesimally small scalar quantity. You can also write epsilon tends to zero and whatnot. But epsilon is a very small scalar quantity, infinitesimal. Eta is a variation vector. That means what I'm trying to say is there exists a path, and that there exists a stationary path, that means the correct solution path, whose at any point, if you get the position vector, is denoted by R naught. Very good. Now you add some random arbitrary eta vector to it. Eta is also a function that changes with a. As a goes, eta changes. And you multiply an infinitesimally small quantity such that you create a variation r which is infinitesimally deviating from the r naught. Okay, this is a standard thing that is even done in gold. So on the other hand, if you go back to the Goldstein's classical mechanics, then you will get this explanation, and it's very nicely explained over there. Still, if anyone doesn't understand, you might ask. But what did we say? I'm going back many slides. Okay, over here we said that there shall be no variation in the starting and the ending point. Did we not? That means at start point it is fixed and the end point is fixed. If the start and end point is fixed, yes, epsilon is a real number. Epsilon is a real number. Okay, we are not talking about anything complex. Epsilon is a very infinitesimally small real number. So, uh, right. Okay, so if my start point and end point is fixed, that means my r vector and r naught vector should be exactly the same at the starting and the ending point, isn't it? Say yes or no. You can type in the chat box. Okay, you can respond. If my r naught and r vector should be exactly the same at the starting and the ending points, then my this eta vector should be 0 at the start and the end points. Okay. So if that is so, then my eta at a initial, what I've written at the last sentence over the last line, eta a initial and eta a final should be equal and equal to 0. Okay. At this point, if anyone has any question with the construction, you can ask. If there is any question with how this has been constructed, if anyone is trying to think, I'm giving you some time to think a minute. Think about the construction. No problem. Okay. So I hope everyone got it. So now we shall move on into the famous F equals ma optics. You can see there is optics in it, the lightsaber, and there is a lot of force being put into this. They are fighting. Star Wars. Everyone has seen, many of you have seen Star Wars. Yes. So fighting with lightsabers. Ah, let's come back into the math part. This is a variation that we have earlier defined. That this is what we want to be for our path to be stationary. Going back once again to show this exact thing which we had come across. See over here in the middle, this one. This is exactly what I have written later on also. Over here. Now I shall be trying to evaluate this. Okay. I've written that I'm doing a partial derivative with respect to epsilon of this entire quantity. That is how I am defining the variation. That means, look at this construction that I've created at the top, which is r is equal to r naught plus epsilon eta. That means this as epsilon tends to 0, my variation in this path length should also tend to 0. That is what I'm trying to say. That means r is an infinitesimally varied path, but this of integral k dr, that means the infinitesimal change in the path length, is what I want to be 0. That means infinitesimal change in the, or you can say infinitesimal change in the phase, in the delta phi. Infinitesimal change in the phase is also what I want to be 0. That means if my variation of phase with respect to epsilon is 0, that means partial derivative of this phase difference with respect to epsilon is 0, then I can say that my path is a uh, follows the stationary principle. That means there is 100% constructive interference between a path and its infinitesimally varied path. If anyone has any questions, you can always ask. So partial derivative with respect to epsilon is what I'm saying to be setting to be 0. Then I apply a normal UV chain rule. Okay, ddx of UV is u dvdx plus v dudx. Simple thing. That's what I get. You can ask, or else I can explain also. I would encourage you to look at this yourself, but you can ask me to explain also. That means what I'm trying to do is that partial derivative of n with respect to epsilon. N is basically refractive index. So partial derivative of refractive index with respect to epsilon means what I have written it as. I have written it as gradient of n dot dou r dou epsilon. Why is it so? If you want me to explain, I can explain. Just you have to listen very patiently. Okay. Dou n dou epsilon. Can we write it as r is nothing but spatial position vector? We can also explicitly write refractive index as a function of x, y, and z. We can, right? We can write the refractive index as a function of x, y, and z. After writing that, what we do is we write dou n dou epsilon as dou n dou x dou epsilon plus dou n dou y dou epsilon plus dou n dou z dou epsilon. We can write it in this way. Then we can write it as a dot product of dou n dou x I cap plus dou n dou y j cap plus dou n dou z k cap, dot product with dou x dou epsilon I cap plus dou y dou epsilon j cap plus dou z dou epsilon k cap. Right? After writing this dot product, the dou n dou x I cap plus dou n dou y j cap plus dou n dou z k cap, that becomes nothing but the gradient of n. And dou x dou epsilon I cap plus dou y dou epsilon j cap plus dou z dou epsilon k cap, that becomes nothing but dou epsilon of r vector, where r vector is nothing but x I cap plus y j cap plus z k cap. Okay, good. Now I have written this dou r vector dou epsilon from my previous slide. Dou r dou epsilon. What would dou r dou epsilon give me? Tell. You can write on the text chat box. What would partial derivative of the radius vector, I mean, sorry, not the position vector with respect to the epsilon will give you? Can anyone say? Eta. Right, exactly. Eta is a function of x. So that is what we will get. That is why I have written dou and dou epsilon as gradient of n dot product with eta. Very good. Now I've tried to compute mod dou RDA, mod DRDA. Sorry. Mod DRDA is nothing but R. I have expanded R vector as R naught vector plus epsilon eta vector. So it just opens up because DDA is a linear operator. Therefore, it works in an exactly linear fashion. R naught and eta are two vectors, and epsilon is a scalar. That's how it opens up. Now this thing is equal to, we know that mod of a vector plus b vector is nothing but root over a dot a, which is mod a square, plus b dot b, which is mod b square, plus 2 a dot b. That is exactly what I have done over here. I have opened it, done a vector modulus. This is simple Euclidean geometry, algebra of Euclidean geometry, nothing else. In a Euclidean vector space, this is something that is very trivial and everyone knows this. We have been doing from class 9, 10 without knowing that what a vector space is. Okay, so this is how it works out. And what we do is that we take that quantity and we do a partial derivative with respect to epsilon. After doing a partial derivative, and this is something you need to look at. It's very simple basically. There is a two factor in the numerator and denominator getting cancelled. And this is how it will turn out. I mean, frankly, if I had a board, then I would have explained it very, I mean, every step. But this is something that you can see. Simple thing. Giving you some time to look at this. Meanwhile, once some of you are done, just write in the chat box. Then I'll move on to the next slide. Okay. Anyone has any doubts in this, or are you still looking? Maybe trying to get yourself convinced. Yeah, yeah. Okay. So let us try to move on further. This is pure simple algebra. I'll give the slides also if you want. And anyways, it will be uploaded in YouTube, so you can pause the video and check out the calculation also. So that's not a problem. Ah, so that is what we have. Now let us, before moving on to the next slide, let me tell you about some notation that I'll be using. The DRDA, that means derivative with respect to A, I shall be denoting with prime. Okay, with a prime. Just like derivative with respect to time is denoted with a dot above whatever vector, scalar, whatever it is denoted with a dot. If it is r vector, then its derivative with respect to A shall be denoted as r prime, r vector prime. Okay. Again, emphasizing that the bold font is supposed to be vectors and non-bold fonts are not vectors. Okay. So the final quantity over here, that is the partial derivative with respect to epsilon of mod dRdA, should give you r vector prime dot product with eta vector prime divided by mod of r vector prime. Okay, that is basically derivative with respect to A, the last quantity which is written in this slide after equals. Okay, so basically whatever results I have obtained in the note part of the previous slide, I have written them down. Integral gradient of n dot eta. Mod dRdA I have written as mod r prime plus refractive index times r prime dot eta prime by mod r prime. Whole quantity times dA equals to 0. This is what it is coming out to be. That means this should give me the path along which the infinitesimal variation in phase is 0, and that is what I'm considering to be the correct path of the light. That means light trajectory. What we do is that this is something standard and done in Goldstein as well. Anyone who is studying calculus of radiation, you can go through this. uh, Second term I integrate by parts, so that gives me See, the point is that this n r prime by mod r prime, this is a quantity which I am considering to be the first function, and eta prime is something that I am considering to be the second function. Okay. So therefore, what will I have? Eta prime means d eta dA. Then that means if you do the partial integration by parts, then this is what you will get. Look at this once. First term remains as it is. Next term is n r vector prime by mod r vector prime dot product with eta. Why eta? Because integral d eta dA dA means integral d eta. Integral d eta means this is going from a initial to a final. This entire quantity n r prime by mod r prime dot eta. This entire quantity is going from a initial to a final because our integral was from a initial to a final. Minus derivative of the first function dot product with that same integral, which gives us eta. This is what we have. Interestingly, do you remember what is the value of eta at a initial and a final? Does anyone remember? Write it in the chat box if anyone does. 0. Yes. So eta is 0 at starting position and eta is 0 at the end position. Why is it 0? Because we are keeping our starting and end points fixed, and we are saying that what will be the trajectory of the light path, keeping that starting and end point fixed. Therefore, our eta is 0. Therefore, this middle term is something that goes out of existence. That is, eta at final is automatically 0. Dot product with anything will be 0. And eta at initial is 0. It's a null vector. Dot product with anything will give you 0. Since eta vanishes at starting and ending points, this middle term, I get rid of this middle term, and we are left with the first term and the third term. The first term is what it is, the third term is what it is, that is what I write. And try to notice that first term there is a dot product with eta vector. This mod r prime is a scalar in the first term. There is a dot product with eta vector, and in the third term as well, there is a dot product with eta vector. Now, we know the distributivity property of this inner product, distributivity property of this inner product over a vector addition, basically. So if this is a dot b plus c dot b, then we can write it as a plus c dot b. This is basic simple distributive law. So in Euclidean vector space, it is dot product and it is distributive over vector addition as well as associative. In this special case, only in this Euclidean vector, this case, it is associative as well. Associative in the sense, sorry, I meant commutative. That means a dot b is equals b dot a. So that is the commutative property. In this case, it is commutative since we are dealing with real numbers, and this is how the inner product is defined. Therefore, if anyone has any problem up to this point, please let me know. Now is the time to ask out. Because after this, we are going to be moving into the main point, like df is equal to ma of t, the main equation. Is everyone convinced? Write yes in the chat box if everyone is. Okay. Muitrada seems convinced. Many other people may not be convinced. I would ask them to go back and look into it. Okay. If anyone is not convinced, they can ask me at any point. Okay. Let us move ahead. Mm, Now, wait. Before moving on, in this equation, is eta an arbitrary vector or a specified vector? Does anyone remember? Is eta arbitrary or specific? Eta is supposed to be an arbitrary vector from our construction. Okay, that just vanishes. The only restriction on eta is that it has to vanish at the initial and the end position. Otherwise, zeta is an arbitrary vector that I'm adding with the real stationary path. That means my solution path. I'm adding eta vector with that, multiplying the eta vector with an infinitesimally small real quantity that gives me the infinitesimal variation from the stationary path that we want. Okay. Therefore, we should try to appreciate or try to keep in mind rather that eta is in essence an arbitrary vector with the only restriction or constraint on it being that it vanishes at the initial and the ending points. Okay. So if eta is arbitrary and if integral some vector dot an arbitrary vector is zero, then what does that mean? Let me remind you about a famous theorem in calculus. You know that, I mean, integral fx gx dx is equal to 0. If I say gx is arbitrary, then can I say that fx must be 0 at all points in the domain in which the integral is being conducted? Both are real single valued functions. Can we say that? I'm writing in the chat box. Integral f of x times g of x dx is equal to 0, where g of x is arbitrary. Where g of x is arbitrary. Then can we say that fx must be 0 at all points in the domain over which we are integrating? We can, can't we? So applying a similar logic, eta being a being an arbitrary vector, only restriction being that it vanishes at initial and final points. Eta being an arbitrary vector, the term multiplied before it, that is also a vector quantity. So that means if eta is arbitrary, that then the quantity which is multiplied with it, I mean dot product with eta, and that quantity must be 0. Okay, see, that is what I've exactly written. I've written since eta is an arbitrary vector function, the previous integral should be 0 irrespective of eta. Hence, we must have this quantity being 0 for the entire trajectory. That means between a initial and a final. This quantity should be 0. Now, remember, our point was to this entire thing was done for the stationary path. That means R should give a stationary path, R vector. That means this is what I'm coming up with as an equation of trajectory. That means a differential equation of trajectory. Okay. Um, yeah, we have already defined A. A was arbitrary at some point of time. I have written here we should try to appreciate the arbitrary nature of the stepping parameter, blah blah blah. No, A was arbitrary at one point of time, but we had given it a specific definition. What was the definition? Mod dRdA equals n. This is how we have defined our stepping parameter to be. Our stepping parameter is such that mod dRdA is n. But we do not know whether A is unique or not. We are not making any claims on that. Mod DRDA is n, or A is some stepping parameter that satisfies this condition. If that is so, then that means mod R prime is n. because drd is nothing but r prime. Mod r prime being n means in the above equation, it's a scalar multiplied with the gradient of n, right? That is the first term. But this scalar is nothing but refractive index n itself. So we can write the first term as n gradient of n in the equation of trajectory under the yellow box. Look at the yellow box. We can write the first term as n gradient of n minus dda, derivative with respect to a, of, now the mod r prime is nothing but equal to n. That means in numerator there is an n in the second term, and in the denominator there is a mod r prime, which is nothing but n. Therefore, these n's cancel out. If the refractive index indices cancel out from the numerator and denominator, then we are left with dda of r prime. dda of r prime is nothing but r double prime, because this prime notation is what we denote for is what we write for denoting a derivative with respect to a. This is what I've said earlier. So my equation becomes what we have below: n gradient of n minus dda of r prime equals 0, or which implies gradient of n gradient of n. See, that I have applied a very smart trick, we can say. I mean, not that I am smart, not that I have applied it. Evans and Rosenquist have already done this in their paper. So the n gradient of n can be written as gradient of n square by 2. This is something which we often do. Like if you have r dot, মানে r vector dot product with r dot, মানে r dot মানে dr dt, then we can write r dot as bdt of mod r square by 2. That means r dot r by 2. This is what we often do, because if you expand the quantity gradient of n square by 2, then it automatically opens up into half n gradient of n plus half n gradient of n, which is nothing but n gradient of n. Okay, that is simple, basically chain rule property only. What I have applied. So gradient of n square by 2 minus r double prime equals 0. Very good. Up to this point, if anyone has any questions, you are free to ask. Please do ask. I am welcoming questions at this point. Because, and if anyone has any comments about how this equation looks like, that you can also say, because it's automatically looking like something familiar. Can anyone make any guesses? Or if anyone has any doubts, you can ask. Type in the chat box, open your mic and ask. Just speak, do whatever. No doubt. Okay, good enough. So I'm assuming, it's a very strong assumption though. I'm assuming that every one of you has understood it. If you haven't, you can go back to the YouTube video when it will be uploaded, or you can ask me also at a later part of the talk. If this is so, then what we'll do, yes, exactly, Shusnato. Very nice. Force is negative of gradient of potential energy, and this negative of gradient of potential energy is nothing but what? Force is equal to what does Newton say, Shusnato? What does Newton say? Force equals mass into acceleration. That means m r double dot, right? So you can write minus gradient of potential energy equals m r double dot. That is exactly where this analogy drops in. Yes. So this minus r double prime, I'm shifting it to the right hand side, and I am feeding you. Basically, gradient of n squared by 2, I have introduced a negative symbol inside and a negative minus sign outside. A minus inside and a minus outside to uh, put it up in the standard format. So I'm feeding you this analogy. Basically, Evans and Rosenquist fed the world basically through their paper. At this point, I'm feeding you this thing after reading from their paper. So we have a classical mechanics, that means basically classical mechanics theory, which is saying negative of gradient of the potential energy gives you mass times acceleration. That means double derivative of the position of a particle. And the geometrical optics says something very weird. What does it say? Negative of the gradient of negative of refractive index square divided by 2 equals the double derivative of the position vector of the light ray, light path, with respect to some stepping parameter A. That arbitrary stepping parameter is still over there. We have not gotten rid of that. But when we'll solve problems, that will be accounted for. So this is how my analogy table looks like. Just try to appreciate the beauty or maybe the bitterness. I don't of this table. Look at this. Yeah, R vector means position vector. The first line, R vector means position vector. We all know. Second line says that P is time in classical mechanics, and we have a quote unquote time in geometrical optics, which is A. It's not time, and it has, I mean, its differential has a relation with time. That means dA equals C by n squared dt. This is something which we had seen many slides earlier. But we have a quantity A, some quantity A. None of us knows its physical significance. I mean, just that its differential is C by n squared dt, nothing else. We have a velocity. In classical mechanics, that velocity is dr dt, which is r dot. And in geometrical optics, that is a quote unquote velocity. You must be very clear in this point that this velocity has absolutely nothing to do with the velocity of the light in the medium. Absolutely nothing. Because dr, it is not dr dt. If it had been mod dr dt, then that would have been the velocity of light in the medium. No. This is quote unquote velocity. That means velocity as per my analogy. Dr dA, not r prime. Mass, whatever the mass we have in classical mechanics, that just gets replaced by 1 in geometrical optics. Very important aspect of this is that you cannot vary the mass in geometrical optics. That means it restricts your optomechanics, as one would like to call it, in several ways. Potential energy in classical mechanics is U, and in geometrical optics, just as you can see, negative of gradient of whatever quantity, that quantity I'm calling it to be analogous to the potential energy in classical mechanics, minus n square by 2. N is a function of the position. N is spatially dependent, refractive index. Therefore, n square is also spatially dependent. Kinetic energy is of course half mv square. We all know in classical mechanics. We exactly apply whatever mass, v, time, whatever we had obtained from the above analogies. We straight away put that in, and we get an expression for quote unquote kinetic energy. Good enough. In classical mechanics, we have what is known as the total energy, m by 2 mod dr dt whole square, plus u as a function of r equals e. And in geometrical optics, we simply add whatever kinetic energy we have obtained in the above previous two lines. Interestingly, why is it zero? Can anyone tell me? Why is the total energy zero? I have written in the geometrical optics case. Look at the expression. Look at the expression for kinetic energy and look at the expression for potential energy. Now define. Now try to remember how I have defined the stepping parameter A. Yes, Shusnato pointed it out right. Mod r prime, that is mod drda, is nothing but n, but the refractive index. That means this kinetic plus potential energy has to come out to be zero. That means there are absolutely no other options there. You see, mod drda is n. So it is n square by 2 minus n square by 2. There is some quantity minus the same quantity. It is giving you 0. Okay, that is why. So you can see two very strong restrictions in the geometrical optics analogy. What are the restrictions? First, mass cannot be varied. It is a single constant, which is 1. And second is that energy cannot be varied. It is also a single constant, which is 0. Try to keep this in mind, that this energy has nothing to do with the energy of the light. No, it is a quote unquote energy. That means an analogical energy. It has nothing to do with the energy of the electromagnetic wave in the medium. No, neither does the velocity has anything to do with the velocity of the light ray in a medium. No, try to keep this in mind. Mass does in no way means the mass of the photon. Okay, no, it's not that. Photon is one. That's completely something different. Let's not dwell into that. I'm saying just to first year students or high school undergraduates, if anyone is there, high school students or first year undergraduates, because they might be confused with this notion of photon, light, energy. Wow, 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 wow. Light has zero energy. If they go to someone and suddenly say, I've learned in the last lecture, light has zero energy, then that is a complete misconception. Okay, I'm just warning you about that. Anyways, let us move ahead. Hmm. It's just a relaxation slide, as one would like to call it. Garden snail is just a punning on the word. Snell's law and garden snail. Imagine it saying, I will go along the shortest path. Really. The law, Snell's law, however, was given by the Dutch astronomer Willebrord Snellius. Okay. So, but before moving on to this part, I should say that now I am moving on to the applications part of this optomechanical analogy. Okay. Primarily because when do you learn the proof of Snell's law? Like, at least in IISERK Kolkata, the proof is taught in second year, first semester. That means the third semester course, and in the waves and optics class. Okay, there is a course named Waves and Optics in physics. In that course, we are taught the proof of Snell's law through various electromagnetic waves, this and that, by using the four Maxwell's equations. Okay, that's a pretty much a detailed calculation. Okay, that's a dirty calculation. That's not dirty if you say, but dirty in the sense for in many cases the calculation is not simple. So you'll get to see that if you use this optomechanical analogy, then the derivation of Snell's law becomes quite trivial. I mean, very trivial it becomes. Let's see. This is a refraction of light, a simple, plain old diagram that we are all introduced in class 8 or 9, I guess. Simple optics. Uh, and the Snell's law says that n1 sine theta 1 equals n2 sine theta 2. Right? That is what our Snell's law says. And n1 and n2 are the two refractive indices separated by this x-axis over here. I'm saying, and there is a constant refractive index above the x-axis and a constant refractive index below the x-axis. Notice that there is a discontinuity in the y profile. That means at y is equal to 0, there is a discontinuity in the refractive index. However, there is no discontinuity in the x profile. That means if you go on horizontally, then there is absolutely no discontinuity. But the discontinuity only lies at y is equal to 0, the vertical profile. So we shall work with this simple toy model to explain our Snell's law, as everyone has always worked with. Okay. Now, one thing to notice is that the brown lines denote d r dA, That means the differential path length. Uh, I mean, basically, not the differential path. It's a derivative of the position vector with respect to a. That is DRDA. That is basically the brown quantity, brown line in both the cases. And the green line is nothing but the dxdA. Because as A is varied, it simply comes down through the red line and then goes through the blue line. Comes down through the red line and goes down to the blue line. Therefore, as A is varied, that is how it varies, and the x varies horizontally, y varies vertically, and the brown R itself varies along that exact same path to which it traverses. Good enough. The differential equation for light path, moving on, is, as I've said, that minus gradient of minus n squared by 2 equals r vector double prime. Since the refractive index n does not change spatially in the x direction, we have the x component of the left hand side is 0. Why? Because n does not change spatially in the x direction. Therefore, gradient of n would be 0. The derivative in all three spatial directions, that will be 0. N is a constant quantity. I mean, at least in x. And we can perform this gradient, and I mean perform this derivative only because it is continuous in the x profile, that is in the horizontal profile. So this simply means LHS is 0, and that forces the RHS to be 0 of our famous biblical equation, trajectory equation. That means d squared x dA squared must be 0, and this implies dx dA is constant. Up to this, no one has any problems, right? If anyone wants to see the previous image, you can. This is the image, and this is where I have reached. Up to this, does anyone have any problem? You can tell me. I'm assuming that no one has any problems. Okay, let us move on. Dx dA is a constant quantity. Now, can anyone tell me over here, looking at just the green line, what is dx dA? Mane, applying simple in terms of dRTA and theta in terms of simple trigonometry. Can anyone tell me what is the relationship of the green line with respect to the brown line and theta? You can just write it in the chat box. What is dx dA in terms of, if expressed in terms of dRTA and theta? Can we say that dx dA is dRDA sine theta? Can we? In one medium, if I say that dx dA equals mod dRDA sine theta? Mod dr, I'm typing it out. Okay. Mod dRDA sine theta. Can we write it like this? Say yes if you agree. Because it's simply that the perpendicular is hypotenuse sine theta. That's basic trigonometry that I would apply. If that is so, then over here dx d is a constant. That means mod dRdA in medium 1 times sine theta 1 must be equal to mod dRdA in medium 2 times sine theta 2. That means this dRdA sine theta, this must be a constant quantity. If this is a constant quantity, then this is what it says. But what is mod DRDA? Does anyone remember? Shusnato just wrote um, in the previous. text in the previous chat. He wrote that mod DRDA is nothing but mod R prime, which is nothing but refractive index in medium 1. Mod DRDA medium 1 means refractive index in medium 1. Therefore, at the interface, n1 sine theta 1 is equal to n2 sine theta 2. Is it not? Our choice of parameter A was such that mod DRD equals n, thus it directly follows that n1 sine theta 1 equals n2 sine theta 2. This is what it follows. See, it just takes 2 to 3 lines of writing. It's not even calculation. You just 2 to 3 lines of writing, which proves the Snell's law directly. This is how powerful this optomechanical analogy is. Great. Now we shall move on into the problem of mirage. Do we have time, Vachoda? Yeah, it'll take 5, 10 minutes, not much. It won't take much time, so just we'll finish it within some time. This is the mirage, the famous mirage problem which we all grew up solving since our school days. This is the trajectory of the optical path. Now I've just drawn a trajectory. Okay, I'm not saying that this is some parabolic or hyperbolic curve or something. No, I've just drawn a path to represent my problem, and that is the x here. The x-axis represents the ground level. The y represents a vertical profile. The x-axis is the ground above which there is a vertical gradient of refractive index. That is, the refractive index vertically changes with height, and the light ray is coming, and it is eventually turning to out. Okay, so how we are taking a toy model in which the refractive index varies linearly with height. Okay, so refractive index varies linearly with height. This is a simple model for that, where n is n naught plus alpha times y, where alpha is some constant. Alpha is a constant that is given, or that we might do take out experimentally. Whatever it is, alpha is a constant in this toy model. Y is the height. N naught is naturally the refractive index at y is equal to 0. That means n naught is the refractive index at the ground level. What do? We now put it into the equation of trajectory. I'm just at this point. It seems like I'm just speaking out, the equation and substituting and this and that. I'll just move on fast. I'll show everything on the put the entire platter in front of you. So yes. Right. We see what I have done is that I have applied the variation of parameters. It's a pretty standard technique that all of us use, and variation of parameters means what? Means you can clearly see that it is a second order linear inhomogeneous equation, right? Yes. So there is an alpha square y term plus an alpha n naught, which is a inhomogeneous part is also not a function of a. It is a constant. So it is a second order linear differential equation which is inhomogeneous. Now there are several methods that you can find in the entire literature. You can my suggestion to high school students or first year, second year undergraduates who have not come across this would be, do not worry yourself too much with this thing. Okay, with how I have come up with this differential equation, how I have solved this differential equation, rather. But what you can do is that you can look up classic texts like Arfk and Weber, solution of differential equations. Where I have learned it from is, I will tell you, it's a very nice source. It's Apostle Calculus 1, Calculus Volume 1. Over there is a famous chapter on solving linear differential equations. It's a very nice chapter. Over there, it is very beautifully explained with proofs, rigorous proof, how you can solve such a type of differential equation. It's pretty simple, trust me. So, I'll not go into the details of that, but you can actually go through this method. It's a very nice method. But the point is that I put my this thing in the equation of trajectory. That means n square I do. After doing n square, I take its gradient in the x direction. That means partial derivative in the x direction and the partial derivative in the y direction. And I compare the components in the left hand side of my equation and the right hand side of my equation. We can one thing we can clearly see that does n depend on x? My question is, does n depend on x? No, n does not depend on x. X has no x dependence. N only depends on y. So n square naturally will not depend on x. Therefore, gradient of n square by 2 in the x direction, that means partial derivative with respect to x, dou x of n square by 2 will also not depend on x. I mean, since n square does not depend on x, dou x of n square by 2 will be 0 specifically. So LHS is 0 in the x component if you are analyzing. RHS is saying d square x d square is 0, x component. D square x d square. That means we obtain that d square x d square is 0 and x is capital A small a plus b, where capital A and capital B are constants of integration. Similarly, we do a similar thing with the y component. We analyze the y component and we come up with a differential equation, solving which gives me this form, a hyperbolic cosine and a hyperbolic sine. Alternatively, you can also write this in the form of e to the power I alpha and e to the power minus, sorry, not I, e to the power alpha a and e to the power minus alpha a. You can write as a linear combination of that also, with this cosine hyperbolic and sine hyperbolic part. Okay, so not much difference. But basically, what we're trying to say is that now we try to set the initial condition. That is what is at our hand. Setting our coordinates such that y is minimum at x equal to 0. Mane, of course, y will have a minimum. If y has a minimum, then at x equal to 0, I'm setting the y to be minimum because my choice of my physics should be independent of my choice of coordinates, right? My equation of trajectory or the nature of the trajectory should be independent of my choice of coordinates. So I choose a coordinate such that y is minimum at x equal to 0. It is similar to my previous slide, this one. You can see y is minimum at x equal to 0, roughly. If y is minimum at x equal to 0, we also put the initial condition, another condition, that x at a is equal to 0 is 0. That means setting a is equal to 0 is similar to setting time is equal to 0. Okay. Setting x equal to 0 is similar to setting time is equal to 0. Nice. And if we put a is equal to 0, at that point we are putting x is equal to 0. We have y at a is equal to 0 to be h. What is this h? H is the minimum height. Okay. Therefore, we have got two equations. X at a is equal to 0 is 0 and y at a is equal to 0 is h. From these two equations, we substitute into the above two boxed out equations and we can clearly find out two of the constants out of four. Found out two constants, we have two more left in our hand which we have to find. Now we can see there are two second order differential equations. That means second order differential equations means that each of them should require two initial conditions. One with respect to its initial quote unquote position and the other with respect to its initial quote unquote velocity. How do we define the velocity? We have y which is minimum at a is equal to 0. That means dy dA at a is equal to 0 is 0. This is how we have put by deciding our coordinates. Okay, good enough. Now our choice of parameter a was what? Mod dr dA is equal to n, which implies dr dA at a is equal to 0 should be The refractive index at height h, that is what I've written. At this point, I'm just reading out the steps. But mod dRdA is nothing but root over dxdA whole square plus dydA whole square, both evaluated at a is equal to 0. This quantity is equal to refractive index at height h, which is the minimum height. But dydA is 0 at a is equal to 0. Therefore, dxdA at a is equal to 0 is coming out to be nh. Therefore, we have two more conditions. Initial conditions for what to say? We can call it velocity. Some call it the Neumann boundary conditions. That is the derivatives you are setting to be specific, constants or some values. Hence, we determine the other two constants, which are a equals nh, n at height h, and d equals 0. This is what we have. So we have determined all our four constants a, b, c, and d, all capital, of course. And now we are ready to write our equation full in its full glory. Substituting the value of the constants, we have obtained x equals n naught plus alpha h times a, and y equals h plus n naught by alpha cosine hyperbolic alpha a minus n naught by alpha. You'll get the YouTube video, so don't worry. This entire video is being recorded. Therefore, you can obviously get back to it at any point of time. Listen to it as many times as you want, and you're encouraged to substitute these values and do this by hand to see how it emerges. Now, as Moitrada was saying about the uniqueness of a, that whether a is unique or not, and I had replied at that time that we would not require a for our equation of trajectory finally. So we would do away with our a, whatever our a is, whether it is unique or whether it is not. That will not affect the physics over here that is happening. Good enough. Eliminating a from the equation. From the first x equation, I am substituting the a because a can be written as x by nh. I substituted the a. I did a little bit of rearrangement here and there, which you are encouraged to try it out at some point. And after the rearrangement, our equation turns up to be something like this. Y is equal to h plus nh by alpha in brackets cosine hyperbolic alpha x by nh minus 1. This is what I have as the equation of trajectory. One thing no one asked, I noticed, is that, let me go back once. While I was showing this, no one asked why dxdA is equal to plus nh and why not minus nh. Right? This is a possible question. Square root of dxdA whole square is equal to nh. That means dxdA can be plus minus nh, isn't it? Is that not a valid question? dxdA can be both plus nh as well as minus nh. My point is that it's absolutely true. And what does dxdA say? It says about in which direction it is traveling. That means quote unquote velocity. How x changes as you change the parameter a. Now dxdA is equal to plus nh would imply that it is going from left to right, and dxd is equal to minus nh would imply that it is going from right to left, nothing else. The x direction quote unquote velocity is remaining constant. Whether you set the constant to be a positive quantity or negative quantity, that's entirely up to you. The form of the trajectory will not change. It also talks about the symmetry a bit, that whether it goes from right to left or whether it goes from left to right, your just equation form would remain unchanged, because all that will change is I guess a sign. It will change only some constant sign might change, nothing else will change. Okay, so dxd might be minus nh, might be plus nh. In both the cases it means that it is either going from left to right or right to left, nothing else. Simple. form of the trajectory remains the same. Interestingly, this is also the equation of a catenary. This is a very interesting idea. That means this is the equation of a catenary. You know what a catenary is. Does anyone know what a catenary is over here? Mm, don't see a lot of yeses or nos, but let me explain it. This is the last slide. So a catenary is nothing but a hanging chain hanging in a gravity, and in our normal gravity, which is horizontally distributed, there is a it changes in a horizontal profile, and in that gravity, if we stick two poles, whatever their height be, it might have different heights, it might have the same height, then the hanging chain would curve out a path, would trace out a path, and that path is what I call, yeah, yeah, it's a special type of algebraic curve. Interestingly, the only thing about interesting over here is that catenary. Where do you see the equation of a catenary in mechanics? If you go on studying mechanics when you go to the third year or second year, wherever, if you study classical mechanics, intermediate classical mechanics, then you will see by solving the equation for a hanging chain in between 2 points, that exactly traces out the equation of that catenary. That means of that geometric curve that Moitura was talking about. So it is much like as if this path of the light is is hanging in warm air. Can you think like that's the exact same equation, exact same trajectory? It's as if the light path is hanging in warm air in a re- uh, in a refractive index distribution profile. It is such that as if the light ray is hanging in warm air. Exactly same equation you find when you solve a mechanics problem where a chain hangs between 2 points or two poles, if you say. That's about it. These are just references. You can obviously go off to them and read extra. There are a lot of things that it covers. It covers central force motion, like as if a planet is orbiting around another planet, they are orbiting around each other. And such things can also be seen in cases of light. So, central forces they have also discussed. They've discussed a lot of things in the paper. I don't have much time, so I showed only two simple examples. And of course, uh, Herbert Goldstein Classical Mechanics. You can obviously go and check them. This is where I would like to end today. Okay. So, and interestingly, this is all that I have. So, if anyone would like to ask any questions, you're absolutely welcome in any of the slides or anywhere. Does anyone have any questions?
Hi, Sayanho. I had a question. Moitra, so Chino, has anybody done Hamiltonian mechanics with the entire system in that paper or recent developments? Anything?
Okay, see, the point is that papers like these go tremendously unnoticed. So, proper Hamiltonian mechanics people have not done on this, and whatever Hamiltonian mechanics exist is whatever Hamiltonian mechanics exist is on the basis of the iconal equation. If you study advanced optics, many people have. I mean, in the advanced courses they teach, I guess, the iconal equation. I have not seen optics courses, but over there, they also approach with a different variational principle, but that is starkly different. That has no direct resemblance to this Newtonian mechanics, but over there, there is a Hamiltonian formulation of light path that people have done, but that is something that generates from the iconal equation. There is Born and Wolf's famous book on optics, where they actually discuss this. which chapter I forgot, but they discuss Hamiltonian properties of optomechanical analogy. They do this, but this exact thing has not been done before, and people have not tried expressing this in the Lagrangian or Hamiltonian form. But yes, that's about it.
Thank you.
Okay, Newtonian. Okay. So inverse square law is something that the paper talks of. Okay, and in such inverse square law type of forces, very interesting things properties have been noticed. Let me give you one example. In central forces, we know that circular orbits are possible in many cases, and in inverse square law, circular orbits are possible. Good enough. In the optomechanical case, in optics, geometrical optics, if you try to put the condition for circular orbit, then it would come out to be an attractive inverse cube law of force, quote unquote force, where circular orbit is possible, and that is the uh, only form of gradient. I mean, refractive index gradient or refractive index distribution where you can find actually a circular orbit. I mean, it's a very strong statement. It literally says that only in minus in k by r format, mane refractive index n is equal to k by r. That means inversely proportional to the radius. Only in this format can you actually find a circular orbit, and that too, this circular orbit is not a stable orbit. It's unstable. If the velocity vector is not perpendicular, velocity mean quote unquote velocity vector is not perpendicular to the radius vector from the center of force. From the center of force, it is not perpendicular. If it is slightly tilted inwards or slightly tilted outwards, then it will either run towards infinity or it will fall towards the center and again go out. Extremely unstable situation. Now I'm trying to do some work on where you can actually find closed orbits of light and what it would imply. Closed light orbits. Would it even imply anything? Like light is perpetually just moving on in closed orbits. Obviously, there will be some energy loss because of light motion and so. Can it ever form? Whether it can or cannot, I'm trying to find a refractive index distribution where this can be found or not. That's it. Thank you.